Dear students, today we will talk about determination of Young's modulus with Searles method. So you can imagine two rectangular bars, say P and Q, that are parallel to each other and they are suspended by means of thin and strong strings. So these strings are thin and they are strong. They are suspending these two rectangular bars P and Q. The wire whose Young's modulus Y you intend to determine is connected between the centers of these two bars. So this is the wire whose Young's modulus you aim to determine. Now what do we do is that if we push these metallic bars P and Q towards each other, what will happen? Obviously, this wire will get bent in the form of a semicircle like this. Suppose this is the angle at the center and this is the radius of the arc, because now this straight wire has changed into an arc. And why did it happen? Because we have pushed P and Q towards each other, right? So this makes the wire bent, and suppose the radius of this arc is now this capital R, and at the center suppose the two ends subtend an angle theta. So what is the total angle? It is 2 theta. We know that the length of the arc is radius into angle. So what is this radius? It is L by 2 theta. Now let us see what is the bending moment. Bending moment is nothing but the torque that has actually bent this wire, right? So that is equal to Y by R into Ig. Remember, Y is the Young's modulus, R is this radius which we talked about, radius of the arc in which this straight wire has converted, and Ig is the geometric moment of inertia. See, generally when we talk about moment of inertia, we guess that it must be something equal to mass into distance square, and that is what actually it is. But if we are interested only in the geometry of the object and not in the mass, if the mass factor is excluded and we are interested only in the geometry, in that case we call it geometric moment of inertia, right? So if you are not aware of this formula, but then we can do it a little later, but for the moment let us proceed. Now let us see what we can do further. So torque is equal to I alpha. You know this is a very common formula, moment of inertia into angular acceleration. So that is Y by R Ig. Now what is this geometric moment of inertia of this thin wire equal to? Again, based on your knowledge of higher secondary level, this Ig is pi R4 by 4. R is the radius of this thin wire, right? Again, I'm calling it geometric moment of inertia because it is not involving the factor of mass. It involves only the geometry of the object, right? Now, I alpha is equal to Y by R. For Ig, I can write pi R4 by 4. And for this R, I can substitute this value, that it is L by 2 theta. So let me do that. So this is Y L 2 theta pi R4 by 4. In all, we get this is Y pi R4 by 2L into theta. So that is what I alpha is equal to. So we can rewrite it on the next page that this I alpha is equal to, this I alpha is again equal to this Y pi R4 by 2L, Y pi R4 by 2L into theta. So we can write it as that alpha is equal to Y pi R4 by 2Li times theta. Now remember, this I is the moment of inertia of the rectangular bar, the rectangular bars that we are suspending on two sides of the wire that has been bent in the form of an arc. So all of you know, based on your previous knowledge, that the moment of inertia of a rectangular bar I is equal to m by 12, a square plus b square, or it is equal to m by 12. I can also write it as L square plus B square. Length square plus breadth square. Length and breadth of the metallic bar. M is the mass of the metallic bar. So all of you are aware of this formula based on your previous knowledge. And I have written this only that you may face a numerical problem in your exam. For this I, you have to write this value, right? Now we know the time period T is equal to 2 pi under root angular displacement by angular acceleration. We know the time period can be written in a number of ways. It is 2 pi mass factor by spring factor. It is 2 pi angular displacement by angular acceleration, right? So you know all that. So that is 2 pi. So because, and why did I talk about time period? It is the time period of oscillation of this. Because this wire produces a twist in the two metallic bars and they start oscillating, right? So it is the time period of that oscillations. So for this alpha you can substitute this factor, and you know that this theta and theta will get cancelled, and ultimately we are left with 2Li by y pi r4. So this time period, and when you square this on either side to get this y, what do you get? This y is equal to, so it is 8 pi Li by t square pi r4. In all it is 8 Li by t square r4. So this is the formula for moment of inertia. You know the length of wire, you know the moment of inertia of the rectangular bar, you know the radius of the wire, you also know the time period of oscillation. So you can easily find the Young's modulus using the Searles apparatus. Now what I aim to show you is that I want to tell you where from do we get this formula. The formula of bending moment or the torque. How do we get it? So let us do that. That's a very simple manipulation. You can do that easily. So we know a simple formula that Young's modulus is stress by strain. Is it? So this stress is y into strain, as simple as that. Now this stress is force per unit area. Suppose dF, small force and small area, y into strain. See, in this case you are bending a wire. You are not pulling it in one direction. You are not pulling it in one direction, but you are bending it towards the side of the radius. So once you are bending a wire, what changes do you expect? You can expect changes in its radius. Suppose initially the radius was r and now it has changed by certain amount, say x. So in this case, the strain will be given by change in length by original length. We know that. So what is this force, small force? It is y x by r dA, right? So, but since we are interested in bending moment in torque, and we know that torque is force into force arm, all of us understand that torque is r cross f, rf, right? Force into force arm. So this will be df into x, torque, what we are interested in, or the bending moment, that will be df into x. So that is y x square dA. What will be the total force? So that will be the summation of this r square dA. This term is called as geometric moment of inertia, what I told you earlier. Geometric moment of inertia. We'll come to it in a next video, but for the moment you need to remember that when we are not interested in moment of inertia with mass term, when we exclude the mass term, and when we are interested only in the geometry of the object, we call it the geometric moment of inertia, IG, and it is given by this. So it involves the radius of the wire and a cross-sectional area, dA, right? So this is the expression for torque, of course, torque or the bending moment, right? So that is how we have used this formula directly over here. I tried to show you that because I thought that many of you might not be aware of this formula. So today we have discussed about determination of Young's modulus using Searles method, in which we have connected two metallic rectangular bars with a thin wire, the wire whose Young's modulus we intend to calculate. These metallic bars are suspended by two thin and strong wires. Then we bend it like this, and then we do these kinds of calculations, as simple as that. So I'm turning the pages again so that you can recapitulate. So this is the required formula, and then on the next page I have shown you that how did we use this kind of formula, right? So that's all.